All right, let's dive into something that honestly feels a little bit like science fiction. We're talking about the power to see inside our own bodies without ever making a single cut. So, how on earth is that even possible? Yeah, think about it. How can you see the actual bones in your body when they're tucked away under all that skin and muscle and everything else? It really does seem impossible, right? But the answer is actually way simpler than you might think.
Okay, so to get to that answer, we need to wrap our heads around something pretty cool. We're going to have to deal with something our eyes can't normally see. We're basically stepping into the world of the invisible.
And here it is. The big secret lies in a really powerful kind of invisible light. And, believe it or not, the simple idea of a shadow. Yep, that's right. When you get right down to it, an X-ray is basically just a super high-tech shadow puppet show. It's all about a special light that zips right through some parts of you, but gets blocked by others.
Okay, so shadows. How does that actually work? Well, the key is this really important scientific principle. It's all about how X-rays behave when they hit stuff, including us.
The word you're going to hear is attenuation. It sounds complicated, but it's not. All it means is that when X-rays pass through something, that something, whether it's your bones or your muscles, slows them down. It weakens the beam. The stained glass window analogy is perfect. Some light gets through easily, other parts get blocked. Same idea here.
So here's how it plays out. You've got the X-ray machine, and it shoots a beam of X-rays at, say, your arm. As that beam travels through, your bone, your muscle, the air inside you, they all weaken or attenuate that beam by different amounts. So what makes it out the other side is this, well, it's a shadow of the original beam. And that's what a detector on the other side picks up to create the image.
And this is exactly why the image looks the way it does. Your bones, which are super dense because of all that calcium, they block a ton of X-rays. They have high attenuation, so they show up as bright white. On the flip side, something like your lungs, which are just full of air, barely block any X-rays at all. That's why they look black. And everything in between, your muscle, your fat, that's where all those shades of gray come from.
Okay, so this invisible light is the key to everything. But that raises a pretty big question. Where does it even come from? To answer that, we have to look inside the X-ray machine itself.
Right. At the very heart of this whole thing is something called an X-ray tube. You can think of it as a special light bulb, almost. It's got a few key parts. There's a negative part, the cathode, that spits out electrons. There's a positive part, the anode, which is basically a metal target. It's all inside a vacuum, so nothing gets in the way. And you need a whole lot of voltage to give everything a massive kick of energy.
So here's the play-by-play. First, we heat up that cathode filament and it starts boiling off a cloud of electrons. Then that high voltage kicks in and bam! It launches those electrons like a slingshot across the tube at insane speeds. They slam right into that metal target, the anode, and it's that incredibly violent collision that converts all their energy into the X-rays we need. Now, what happens in that collision is actually pretty wild. There are two main ways X-rays get created. The first one, which accounts for most of them, like 80%, is called Bremsstrahlung. It literally means breaking radiation. An electron flies super close to an atom's nucleus, slams on the brakes, and has to get rid of all that extra energy, which it releases as an X-ray. The other way is called characteristic radiation. This is more like a game of billiards. The incoming electron smacks into one of the atom's own electrons, knocking it out of orbit. Then another electron from a higher orbit falls down to take its place, and when it does, it releases a very specific X-ray.
So to really get what's happening in that collision, we have to zoom in. I mean way in. We're going down to the atomic level, to the fundamental building blocks of everything.
And of course, we are talking about the atom, the smallest possible piece of matter. You've got your nucleus in the middle with protons and neutrons, and then you have electrons zipping around it. This tiny little thing, this is the engine that makes the whole X-ray process work.
A really helpful way to picture this is the Bohr model. It imagines the electrons aren't just in a random cloud, but in these nice, neat orbits or shells around the nucleus, kind of like planets orbiting the sun. And the key thing is, electrons in the inner shells have less energy than the ones way out on the edge.
Okay, so here's the magic moment. Remember that characteristic radiation we talked about, where an electron gets knocked out and another one falls down to replace it? Well, when an electron drops from a high-energy outer shell to a low-energy inner shell, it can't just keep that extra energy. It has to release it, and it spits it out as a single particle of light, called a photon.
In an X-ray tube, that energy drop is so massive that the photon it releases is an X-ray photon. That's it. That's the birth of an X-ray. All right, let's pull all these pieces together now. We're going to connect this atomic-level physics back to the real world of getting an X-ray image, and maybe most importantly, talk about how we handle all this power safely.
Remember attenuation from the beginning? Why bones block X-rays better than muscle? It all comes down to the atom. Materials with a high atomic number, which just means they have a lot of protons in their nucleus, are just better at interacting with X-rays. That's why we use tungsten with 74 protons as the target to make the X-rays. And it's why the calcium in your bones, which also has a relatively high atomic number, is so good at blocking them. It all connects.
Now let's talk safety, because this is powerful stuff. The single most important rule to remember is something called the inverse square law. It sounds technical, but the idea is simple. The further away you get from a radiation source, the safer you are. And it's not just a little bit safer, the intensity drops off fast. Like if you double your distance, the radiation intensity drops to just 1/4 of what it was. It's a huge difference.
Let me give you a practical example. Let's say you're standing 16 meters away from the X-ray source. The intensity you'd feel is about this much. We can call that our safe baseline, a really low number.
Okay, now what happens if you just move closer? Let's cut that distance way down to just 4 meters away. The intensity doesn't just go up a little, it skyrockets. Look at that number. It's 16 times higher. That is the inverse square law in action, and it is exactly why distance is a radiographer's absolute best friend for staying safe.
So there you have it. From a simple shadow to the incredibly complex dance of electrons inside an atom, the X-ray is just this amazing example of how we've learned to use the fundamental laws of physics to help ourselves. It really makes you wonder, doesn't it? If physics gave us this unbelievable window into our own bodies, what other invisible worlds is it going to let us see next?